2002 Mercury Cougar with a 2.5 liter engine. This is one of our evening students' vehicles. Story with the car is he went to leave and the vehicle didn't start. He drove it to school, no problem, did not start afterward. So I had my class check this out, and what I did first is I had them watch my two-part series on electronic returnless fuel systems that Ford runs, and I'll throw a hyperlink in here so you guys can see the two videos that I've shot on these systems before. So I had them watch the videos and I had them do the troubleshooting on their own and describe to me what they found, the tests that they did, and based on the test results that they had, they came to the conclusion that it had a bad fuel pump. And I was in agreement with them. Now this vehicle came back to me after the pump was installed and it still does not start. So the question is, what did we do wrong? Okay guys, I have the scan data pulled up on the screen here. What we want to look at on this system is our fuel rail pressure. We can read this because this is an electronic returnless fuel system, unique to this design. Don't expect to see fuel pressure on scan data other than this system, or really when you start getting into the newer GDI systems, then you'll have some fuel rail pressure readings. But it's nice because we can look at scan tool while we're cranking it, see if we have fuel pressure. Maybe this car has another problem. So take a look at that guy right there. This is our pressure reading, and it comes from this voltage reading of that fuel rail pressure sensor. Very slight pressure changes have occurred. This is 0 right here, this is 0.2. So a little bit misleading that it's a very large, looks like a very large increase. It is not. Things to pay attention to. So we definitely do not have fuel pressure. So the next thing is we have to go back to this fuel pump driver module, which my students have checked previously, and see what we have as far as signals, grounds, powers, and we'll go from there. Here's the fuel pump driver module. I've removed it from its location for easier testing. It actually sits behind the driver's seat on the B pillar on this Cougar. And the first two wires that we're looking at is the power and ground. That would be this orange or green with an orange tracer, and this, I believe it's a solid black wire. So I'll get you up on the screen and we'll take a look at it. Okay, nice thing about the Varus is how easy it is to bounce between the scan tool and the scope. Just hit the home tab down here. Come right over here to our scope multimeter, and what we want to do, I'll show you the setup. We'll go to our 4-channel, and we're going to turn basically channel 1 and channel 2 is all we're looking at. DC volts for both of them. 20 volt scale. Channel 2 is my pump ground. Channel 1 is my power feed. Sorry, I said pump ground. Channel 2 is my module ground, channel 1 is my module power feed. Throw up a voltage scale here too, you can look at live. So this is 12.8 volts. I have a battery charger on this, so we have a little bit of up down here. I think for this one, a time-based setting of 5 milliseconds is probably too fast. Really a 1-second screen is probably pretty good. You can really see those battery charger oscillations there. You're going to have to ignore that. As usual, we have a dead battery here. So watch these numbers here, watch the 2 here. I'm going to crank it. So that looked pretty good. Some of you might not like this 7.8 volt number here on a crank. Remember, the battery's very, very weak. I have a charger on it. Initial cranking amperage can exceed 600. I've seen them as high as 800 amps on initial crank. I don't have a problem with that. This is a good power and ground for this. We can look at the initial turn on. It's right there. That was your 7 volt, 7.8 volt right there. This is not a problem. I know when we were doing this earlier, and I had my students doing this with me, and they've gone home for the day, but I had them check this main power, and they were concerned that they had 10 volts on that wire, and this is, you know, something that you need to think about when you're doing cranking circuit tests, is the starter's going to drop system voltage drastically. So they didn't like 10 volts when I told them this should be battery voltage. You have to consider what you're doing with the car. Cranking it over 10 volts on a feed wire is perfectly fine. So what we know so far, this module has a good power and a good ground. The next two wires we're looking at are the pump motor control wires, and that's this white black and this brown with the yellow, maybe tan with the yellow. And we're not sure of the controls yet, but we'll find out here in a second. Okay, this is frozen from our last capture, so we'll unfreeze this. And what we're looking at again, channel 1 is our fuel pump power, and channel 2 is our fuel pump ground, or vice versa. We're not really totally sure. What we can say though right now is that this pump is ground side switched. And we know that because both of those pump wires are showing 12 volts. Let's take a look at the wiring diagram on this for a second, on this circuit, because I want to talk about the differences with this fuel pump circuit as opposed to others. Okay, if you take a look at this diagram, here's the two wires that we're testing right now. We're checking them at the module, and that would be this brown yellow and this white and black. And what we find with this design that's unique is the fuel pump relay circuit. Well, of course, this whole fuel pump driver module is unique, but this fuel pump relay is completely different in operation to just about every other relay out there. Most of our fuel pump relay circuits are computer controlled. So this wire that we're looking at right here, this would typically go to the PCM. And the PCM would control the coil for the relay and close the contact, which would send power to the fuel pump. The computer would look at RPM and key on inputs to know when to turn that fuel pump on. Not the case here. You look at this diagram, what you see is we have power coming from, actually this got moved, can't really see this, from power relay. I wrote that. The main power relay sends 12 volts into this. Now if you know anything about Fords, when you turn the key on a power relay, that circuit powers up. It's not computer controlled. So basically what we have here is an ignition input. As soon as you turn the key on, we get power on this coil. This coil has a ground all the time. So as soon as you turn the key on, this thing makes a magnetic field, pulls the switch closed. From there, so we're sending power on this green-orange wire. We send it through the inertia switch. And what would typically be on the other side of the inertia switch would be the fuel pump, not the case in this design. If you follow this other green-orange wire right here, you can see that it comes into our fuel pump driver module. They have that listed as ignition. It's one of the two wires that are actually worded properly on here. These are mislabeled. Something else that can throw you off as a rookie. So this ignition feed, that is the main power to this module. That would be what turns this module on. When it receives 12 volts here from the inertia switch, which gets fed through the relay, we power up this module. You see our main ground right here. I've shown you those already. Our main power, our main ground is good. We have 12 volts coming in here, and we have 0 volts on our ground. We did loaded circuit voltage drop test on that ground. So what that tells us, no problem with the relay, no problem with our inertia switch down on the bottom of the page. And so we're continuing. And now where we are connected to these two wires, one right here. We're reading 12 volts here, and we're reading 12 volts here. These are the two pump wires. So just to highlight these for you guys, these are the two wires that we are now connected to. So we can say a couple things about that. I think right away we know that this is going to be ground side controlled. So this module is going to switch the ground for this pump circuit. Now it would help if this wasn't mislabeled in here. This says sensor signal, this says signal return. Look, fuel pumps aren't sensors. Those shouldn't be worded that way. But what we can take from this, a signal return on a sensor is always the sensor ground. Now we can assume that this brown-yellow wire is the pump ground, and I say we can assume that in this application because we're not going to jump it or anything, we're just going to measure it. But that's going to be the one I expect to drop, mainly because of this signal return designation. Now I could be totally wrong because truthfully it shouldn't be worded this way at all. Sensor signal, it's not a sensor. So I don't get that. That's a major mistake there. We're going to watch these two. When we crank this engine over, if this module is doing what it should be doing, I believe that this wire is going to drop to near ground. Something else while we're here before we crank this over and I show you that. The engine computer talks to this fuel pump driver module on two wires. This fuel pump module wire right here on pin 40, it's a green and black, and this fuel pump module wire pin 54, it's black with a blue. So those two wires would be the communication wires, and they have them listed as ignition. That's wrong. Black and blue, that says switched ground. That's wrong too. So these designations are horrible. I will put a link in here for the other video that I did on the Ford systems like this. It's actually a two-part series. It was a case study we did out in the field. We actually had a field trip. I took my students that day to one of the garages I work for, and we did a live vehicle. It was a no start. It was one of these, and I used some different procedures. Still the same stuff. And then the next day we came into class and we talked about it, and I shot the follow-up video. I think both of those together combined with this one should really give you a good understanding of how to check this system. And so really the wording up here, we have some help, and that's going to be those other videos. So not knowing right now, for some of you, not knowing what these two wires should have, I don't want to jump to the computer's control wires yet. I really just want to know what this pump's doing. If this pump turns on, switches to ground, then we're really not worried about monitoring the two computer control wires. So let's take a look at it. I'll crank it over, see what it does. Okay, there's our reading. Again, the ripples in the screen. I have a battery charger on this. I'm going to crank it. You guys can take a look. Okay, this was the event. This would be where I first turned the key on right here. Sorry, this would be where I first started cranking. See my green trace drop very low. It has some spikes in it. Red trace is staying pretty steady. Has some oscillations. Again, battery charger and starter current. Remember, cylinder compression is going to change what that looks like. So our feed looks good to our pump. We are getting a ground, although it is a pulsed ground. And then at this point, I believe I stopped cranking where this voltage rise is here, and the pump is allowed to continue to run for maybe about a second and a half, maybe 2 seconds, and then the pump shuts off here. And what this would be, this line increasing slowly, would be the pump itself. That'd be counter electromotive force or counter voltage you're looking at right there that's causing that slow rise back up to battery. So this pump, looking at this picture, especially that right there, is really showing me the pump is spinning. It's a brand new pump. If we look in this area closer, which I'm going to have to change my setup to do this, Yeah, let's do that. Let's retake this capture while we watch this ground area a little bit closer, a little bit more detail. So I'm going to drop my time base to do that. I'll drop that down to a very fast time base. We'll watch this green trace. I will peak detect it, which jacks its sample rate up. And this might be a little bit difficult to do by myself. I will freeze it over here. Okay, that's zoomed all the way out. That's zoomed all the way in. This would be the capture that I just took. And what we're seeing here, power, ground, we have pretty much a full ground and then it's letting it go, full ground, letting it go. This is a pulsed fuel pump. This is how it works. It controls fuel pressure by pulsing the ground at varying duty cycles. So the longer the on time down here, the lower portions your on time, the longer your on time would be the higher the duty cycle, would be the higher the fuel pressure. Now the last one that I showed was not pulsed during cranking. The captures that I have in section 15 in my book, Fuel Electrical Circuit Designs, is not pulsed during cranking. I don't think this is a problem. I should still have fuel pressure on this. This is a very long on time. If anything, maybe 90%. We should have fuel pressure here. Why don't we? Okay, I think the next thing that I'm going to show along with this, we're going to throw in a third channel here. And that third channel, we're going to make this our, I'll have to unfreeze it. We're going to make this our low amp probe. And I'm going to show us our fuel pump current. So I'm really just going to take that. I'll get you a shot on the car. As far as where I'm going to set this amp clamp, there's actually 4 places I can do it. If you think about this design, I could grab the main feed, this green with an orange. I could grab the pump power feed, which is the white and black. Remember that this module gets powered up, then the module sends power to the pump, and the module also grounds the pump. So I could go on this tan with the yellow or brown yellow, and then I could also go on this main ground right here too. So I really have 4 places to put my amp probe to measure fuel pump current. I'll just go on this white black. It's pretty much open here and I can get the jaws of my amp probe around it. Setting this on a 20 amp setting on the amp probe itself. Hit the 0 button, take you back up on the board. Okay, we're all set up. Pump power, pump ground, pump current. Amp clamp set on a 20. I think we'll peak detect this guy too. And we'll set this to a 10 amp. Typical fuel pump current would be less than 10 amps. Typically, I'm going to crank it and I'll freeze it over here and we'll take a look at it. We'll zoom out on this capture. Some of you guys have wondered how to zoom with the Verus, and the way that you have to do it is you take really fast time-based settings and then you let it roll with the buffer, freeze it, and then when you zoom, you're actually zooming out on the Verus, not in, as other scopes. Blue trace, the average here that you see is your pump current. Of course the spikes are in there too because we're making and breaking the ground. Pretty tough to make heads or tails out of that. Pump power is good. It is a pulsed pump ground. We've looked at that one. This is my pump current flow, and what we don't like right away is this current is roughly a 0.5 amp to 1.5 amps. In fact, we could get a min-max here. Oh, I didn't catch a max. This is a frozen picture, but I'm telling you, you can look at it here. 2 amps at most that we're seeing on this fuel pump. So what can cause low amperage on this? We could have high resistance. We could have a bad pump ground, which we don't. We could have a tank that is empty. We could also have an issue when it was installed. Something else that I think I want to show you guys here. This is an 8-bar fuel pump, and what that means is there are 8 bars per rotation. That's those commutator segments. If you look at the top of a fuel pump, you would see something like this, and we would have these sections or segments. We would have a brush that rides here. We would have a brush that rides here, positive and negative, and then this thing's going to spin. And so these humps that you're seeing here would be the commutator segments. Maybe a side view would be, this is the body of the motor. You'd have a brush riding here and a brush riding here, and this thing's going to spin. So knowing that this is an 8-bar pump helps because of all this noise in here. So I can place my cursors at 8 of these humps, and we'll see if we can see a unique characteristic in here. It's definitely hard with all of these hash marks. Count this as 1, 2, 3, 4, 5, 6, 7, 8, and then this would be repeating itself right here. So again, 1, 2, 3, 4, 5, 6, 7, 8, back to 1. Take your time difference. We can actually see some repeatability here too. This one's a little bit low. This one's a little bit low. Right after a high one. Very tough to pick it out here. My time for this pump is 7.15 milliseconds. So I have 1 rotation of this electric motor occurring at 7.15 milliseconds. What we can do with this number, we can actually figure out our RPM. Now, to figure out revolutions per minute, you need to understand that there are 1,000 milliseconds in a second or 60,000 milliseconds in a minute. So what we need to do is take 60,000 and divide it by 7.15. The number I come up with, 8,391 RPM. Now there's a bunch of numbers after this. 8,391 RPM this pump is running at during a cranking situation. And that would be with 10 volts available to the pump, a little bit of a pulse ground. That is a ridiculously high number. That is more than double what it should be for this situation. 4,000 to 6,000 in that range. I don't use pump speed a lot. This will be an application where this is going to help us. I'm going to do this one more time, but what I'm going to do now is I'm going to manually ground this pump so we can get rid of all this noise, and we can take an amperage measurement and we can take an RPM measurement. We'll be able to see those unique characteristics a little bit better. So I'll get you a shot of how I'm doing that. We'll come up to the screen and we'll redo this one more time. I have my jumper wire attached to this metal bracket back where I have my multimeter ground, and helps to know what you're doing for sure. We don't want to ground the wrong wire here. We could actually fry this module if we did. This white and black is the steady power that this module sends to the pump, and the brown and yellow is our pulsed ground. And so I'm just going to put the jaws of my amp clamp around my jumper wire, take the other end, and I'm going to ground this pin on the module. If you listen carefully, you'll hear the pump turn on. See if we can hear that. Take the jumper wire off, let you listen. Pretty sure the camera caught that. So pump is running. Come back up to the screen. I'll show you what this looks like. Okay, I want to try to do this part pretty quick. I don't want this pump running for a very long period of time like this, mainly because I know what's wrong with it. And this is our unfrozen picture. You see our full ground here. Not that you needed to see that, but there's your feed, there's your ground. Remember, I'm grounding it myself. This is our pump running right here. Freeze this picture. Actually, let's do this first. Let's unfreeze that. Go to our home tab, scan tool, fuel rail pressure. Notice, still 0 PSI, no pressure on the system. Back to our scope. Pump's running. Pause that picture, take a look at the buffer. I'm going to unground this. And you see our overall average, about the same, 0.5 amp to 1.5 amps. So giving it a full ground really didn't change it much as far as amperage goes. Remember, it had a little bit of a pulsed ground before. And this will be one where we look for unique characteristics. Now, we really couldn't see that before because of all the noise from the pulsed ground, but we can definitely see one now. There's one here. Actually, we see that there, but that's not enough. So that can be misleading. 1, 2, 3, 4, 5. This is definitely more than a 5-bar pump, or sorry, 4-bar. So maybe we don't use that one. We know it's an 8. How about this one right here? Really, this has the best signature. It's pretty tough. This isn't an exact science when you're looking for unique characteristics in a waveform like this, trying to determine how many bars are in a fuel pump. They can be 8, 10, 12. Most of our domestics are 8, although we just did one recently that had 10. So we use this point. I know it's not that one. That's not enough. If we're counting right, it's going to be that one again right there. And we should have 8 in between the cursors. If we did this right, and let me get these cursors set up. I'll put it right on the point of that. Kind of tough to do here with the smart board. Put it there, there. We'll count them. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. This is definitely an 8-bar pump. Time difference here, well, that's a lot faster. Look, 5.6 milliseconds now. So we take 60,000 here. It's going to be 60,000 divided by this number right here, which is the time between my cursors. This would be one rotation of this pump. 5.60 milliseconds. Do the math. That's awesome. 10,714. And of course the decimals here, there's a whole bunch of numbers, you guys that are doing this with your calculators. 10,000 RPM this pump is running at. So when I saw that, at this point, I had to ask the guys that put the pump in if it was one of the pumps that was cut and wired in. And it was a different group of guys that did this, and so I'm not worried about it that this happened. It's not a big deal. This was a perfect learning situation. And I'm not going to point fingers at who did it and what. But my question to the other group was exactly that. Was this a direct fit pump? Did you just plug it in, or did it get rewired? And what I was told is this was rewired. So now think about this for a second. 10,000 RPM. What's going to make an electric motor spin that fast? 4 to 6, typical. There's no resistance. When an electric motor spins that fast, it produces so much counter electromotive force. That's why your amperage is very low. So the reason our amperage is so low is because our RPM is so high. Our RPM is so high for a few reasons. Maybe the brand new pump has an impeller that fell off. Not the case here. Maybe our brand new pump was wired backwards. So this is actually pushing instead of pumping. If it's pushing, it's really just pushing air. We have no media there, no fluid, nothing to slow the impeller down. If the impeller slows down, the pump motor slows down, your amperage is going to rise. This thing was wired backwards. So I'm going to take you over to the module and show you how we temporarily fixed this to see if this was actually it, and we'll go from there. One other thing, it's very important before I get off of this. I would never suggest that you take one of these systems and give it a full ground outside of the computer system. And the reason why is fuel pressure is being controlled by pump speed. If you take a good pump and you ground it on this system, you'll jack your fuel pressure up very high. It would be damaging for the pump, and they do put blow-off valves in the tank or a pressure relief valve that's in parallel to the pump circuit, so that would help. But this isn't something that you would do if you didn't know that there was no fuel pressure. So you guys saw we went and checked our fuel pressure with this jump that was at 0. Let's be clear about that. I'm not suggesting we do this. I'm really doing this to clean up this amperage pattern and show you guys how to do a pump RPM measurement and how valuable this was in troubleshooting this vehicle. Okay, I'm not sure how well this is going to show up, but I'm going to try. Okay, think back with what we're doing here, guys. We have a pump power here and a pump ground here. This is a controlled ground. And remember, the module supplies power here and grounds it here. So even if we were wrong, let's say that the pump motor is not wired backwards, and we would have to drop the tank to find out. But let's say we were wrong and we switched these two. Would we damage this box in any way? The answer is no. You would just spin the motor in the opposite direction. So I have no problem, even if I'm wrong in switching these, I have no problem with this module. It can handle it. There's no danger here. Now, you wouldn't want to mix this up with any of the other wires. You would have to know what your two pump wires are. We're safe in doing that. So I'm going to put this brown and yellow over here where the white and black is, and the white black where the brown and yellow is, just as a temporary, so I can really show you guys what's going on with this car. So I'm going to unplug this connector. Next thing we need to do is we need to pop this red clip out of here. And where's my pocket screwdriver when I need it? It's kind of funny. I get on my guys all the time about pocket screwdrivers. Where's your pocket screwdriver? It's one of the must-have tools for my class, and I didn't even have one with me. This isn't even the one I wanted to use. Go figure. It's too big of a screwdriver. Need to get this red clip out of here. This is what holds the locking tabs from moving. So pull that guy out. Remember which two we're pulling out. This white and black, brown, yellow. And this part I'm not going to be able to show very well because these clips are in there pretty well. I have to release it and pull at the same time. It's not easy to do, especially when you're trying to film. Watching the camera, watching my fingers. Okay, got that one. Nope, had it. Pushed it right back in. Alright, there's my white black. Pump power. I'm just kind of tugging on the harness to pull it out. Okay. So switching the location of these. Now here's the thing. We definitely don't want to leave it this way, because what will happen down the road is when this pump fails in the future, whoever wires this again, if they don't wire it the same way, if they wire it how it was supposed to be wired, then the new pump will run backwards. So these are reversed right now, and we will redo our tests. So now my white black is my ground, and my brown and yellow is my power. And this is something I do not want to do now. I don't want to re-ground this. The reason I do not want to do that is I don't want this pump running at that kind of pressure. So I will put the amp probe around it. We will watch the current, and we can watch the controlled ground too if you guys want to. So we'll watch our pump ground voltage, and we'll watch our pump current. I'll get you back up on the screen. Okay, if we did this right, this vehicle is going to start. And before I do that, I want to talk about the differences in what we're going to see. This is not going to look the same. We probably are going to have a very difficult time measuring pump RPM with this thing running. Remember that pressure is controlled by pulsing the ground. And I know I didn't show the computer control signals with this video, and I'm not going to. I have 2 other videos that show it. Also, you can refer to section 15, which is fuel pump electrical circuits. I have a nice description on this system. And I'm not going to show the computer controls because I don't need to for this. I just want you guys to understand when we start this car and after measurement, I'm not sure we'll be able to do. And I haven't tried this yet, so up to this point, I'm really retracing all of our steps. And now we're working live together. So I'm not sure what this will look like. I know the car is going to run. Watch the screen. Let's get our bearings here. Turn our cursors off. There's my amperage scale. This is pump amperage. I don't have this one connected right now. This is my pump power. Don't worry about that. Our pump ground voltage, that's this one. This should go, as soon as I turn the key on, this should go to 12. Remember that the pump ground actually looks like power with just the key on. So I'll turn the key on, that number is going to rise. We'll look at that first, make sure we're connected. That was a prime that you guys just saw there. So this is our pump ground. Again, pump current. Let's see what kind of scales we're on here. 2 milliseconds. Yeah, we can go with that. 10 amps. I'll start it, and I'll probably have to freeze it over here, guys. Our amperage is a lot higher, isn't it? We're around 3 to 5 amps in that range. And that's going to vary based on fuel pump system pressure. You get a number right there real quick. Fuel system pressure, I'm at 40 psi right now with a fuel pump rail pressure voltage of 2.81, so there's some useful numbers for some of you guys for a later point in time. Notice this fuel pump monitor keeps switching off and on, off and on. It was doing that before. That's a non-issue. I'm really not sure why that would say that. There's no fault listed here. Back to our scope. Let's pause that for a second. Shut this car off. Pulsed ground again. Again, if you want more information on this system, you guys got to check out those other 2 videos. I'll throw the links in here. Pump speed, It's going to be difficult to do because of the spikes. I'm not sure this is even going to be accurate, because if you look at this area here, this would be the on of the pump. This is the off of the pump, and so what happens now, our waveform characteristics of our humps are really blurred in here, because think about this, we're actually turning this off or on and then off. When the green trace is low, when this green trace is low, notice we have an amperage rise, and when the green trace is high, that's off, we have an amperage drop. So this is on and off with the pump. So these high lows of this are no longer the armature or the commutator segments. So measuring pump current right now really cannot be done with this picture. I would have to jump it with the jumper wire, and I can't do it. So I apologize, I cannot do a measurement for RPM here. If I'm wrong, please correct me. I'm pretty sure that the high-lows, I mean, you can see it here, guys, the high-lows of this ground correspond exactly with the current, and so I can no longer see my commutator segments. I may be able to catch this on a full ground, say on initial turn on, so let's see if I can see that. What I'll do for that is just turn the key on, we'll get a prime, and on a prime we shouldn't be limiting pressure. Should be a full ground. Get an initial key on. Not sure if I caught that event. See what it looks like on initial key on. I think pressure in the rail is going to determine what this looks like too. So if our rail pressure is at 0 as opposed to rail pressure at 40, the initial turn on may not be good. And I missed that event. Let's try it again. I froze it over on the screen, not up here. Okay, there's my initial turn the key on right here. Is where I turn the key on. I'm going to zoom out on that a little bit. This is initial key on, so we have not grounded the pump yet. This is a very small time frame from the time I turn the key on here to the time where this fuel pump module decides to ground this. Between those two cursors, this is a time frame of delta time, 40 milliseconds. So this might look like a long time right here. This is 40 milliseconds from the time I turn the key on to where the pump starts to get a ground. And we want to zoom in on this area. It looks like it's pulsing it right away, and I believe the reason why, this car has not been sitting at all, and my fuel rail pressure is good. It's already sitting at 40. I shut the car off. There's probably not a bleed down issue on this. I haven't looked. I don't know if I have my key on. I'll show you. Yes. My key is on as I've been talking here. See what our fuel rail pressure is. Yeah, see, we're even higher pressure right now. So I cannot show you a pump RPM on this without redoing my jumper wire test. And if I redo my jumper wire test, I'm really taking the computer out of the picture here. And we're only grounding this, it looks like about, see what our duty cycle is here. Kind of tough to see it with this capture. I'll redo it one more time at a smaller time base. Go back to 2 milliseconds. Get you the shot. Remember, on time is the low portion, off time is the high portion. So if you look at this, really need to be even on a lower time base to really see this. Let's start this one more time. Let's go Let's go down to 500 microseconds. And I'm going to start the car. I know this is running. It was pretty much the same on a key on. And the reason I took this picture for you guys is so you can see that my on time down here is much smaller than my off time. So when you measure duty cycle, what you're really measuring is within one cycle of a signal from right there to right here. So the trailing edge to the next, sorry that's too far, to the next trailing edge. Trailing edge signal, leading edge, trailing edge. So trailing edge to trailing edge, it's just where I just decided to measure. This would be one cycle, and the way that you would look at this would be from here to here would be representation of 100%. Notice this area where we are low is much smaller than where we are high. If I had to guess, I would say that that is less than 20% duty cycle. In other words, we're only grounding this thing 20% of the time. So picture that if I would put my jumper wire on this, what kind of pressure would we have? We would have extremely high fuel pressure. I'm not going to do it. So lessons here. Fuel pump current, it's another test we need to add to our arsenal of tools. Fuel pump RPM, it's another one that we need to add. We don't always use it, but I have to tell you, fuel pump RPM for me was the one that said, hey, this thing's got to be wired backwards. 10,000 RPM, it's crazy. Granted, the electronic returnless systems, if this car's running, guys, you're not going to do a fuel pump RPM measurement on a running returnless fuel system. Unless the computer's giving it a full ground and there's a low pressure problem, these add variables to it. Definitely valuable to do. Something else I want to point out before I end this, I know this was long, but this was a good one. What I want to point out to you guys, I gotta turn the key back on. What I wanted to point out was the code that was in here. And there may be some other codes now because I had that module unplugged. Let's see what it shows me. There are. I unplugged it. So we have some extra codes. Guys, when we got this car back from the other group that worked on it, the code that we had was this guy right here, this P0190 trouble code. And this is again a chance for me to gripe about manufacturer flowcharts. This code, if you follow this code, it has you checking the fuel rail pressure sensor, has you checking the wiring and the computer. And there is no mention of low fuel pressure for that trouble code. That code is being set by low pressure. So, you know, it's no wonder that mechanics in this field have such a hard time, especially starting out. What do you do when you get a car? We are programmed to look at the trouble code first and then go from there. I mean, I do it myself. Had you started with this trouble code, you would have possibly put a fuel rail pressure sensor in this, and then maybe a computer after that. The guys that don't know how to do diagnostic work, think about where they would have gone. They changed the pump, and by the way, the pump was the right call. So I know my student that did the original diagnosis, he's not here right now, but this is an attaboy to him. Nice job, it was the right call. Problem was, when the pump got put in backwards. So, imagine you're at a shop, you don't know how to do diagnostic work, you threw a pump at it because you didn't have pressure. Now what do? This is a pretty complicated system. Next thing you probably do is you throw a module at it, that fuel pump driver module. And guess what? That didn't fix it either. So now what? Pull the codes out of it, maybe you forgot to do that, you got this fuel rail pressure sensor circuit fault, so then you put a fuel rail pressure sensor in it, that doesn't fix it. Continue to set that code, by the way. Then you throw a computer in the car and it continues to set that code. God forbid, maybe you put a wiring harness in the car too. Think about how much you're in over your head when a simple understanding of the system, how it operates, how to test it, how to use a scope on it. And I know all the procedures that I've shown here, you know, you guys might have picked a different path or done it a certain way or did it a different way than I did. But you have to remember what I'm trying to do is show you guys as many testing methods as I can. And that's what we did. And I hope you guys like that. I really think that this one was really cool, and I really think that if you don't follow what I'm telling you to do, if you don't educate yourself, think about how bad this scenario could have been with a confirmed bad fuel pump that ended up having the wires crossed. And you know, in the field, this might have been at the third garage and you would have never known that. Final fix for this car, we need to drop the tank, rewire this correctly, put it back together, and then switch our leads again. I'm not going to leave it this way, but I wanted to show you guys the fix on this vehicle. Ford electronic returnless systems, guys, look for similar designs coming up on our GDI systems. They're doing that. I was in a real nice class this weekend, ASA conference. John Thornton, Scott Manna, great presentation on GDI systems. And they're doing similar stuff on their electronic returnless systems. They're using low pressure sensors, high pressure sensors. So similarities here, guys. Look for them. More on the way.